apart from the El Nino Southern Oscillation, the surface circulation is quite robust in the Pacific Ocean. And here's a sketch of this. A robust wind-driven surface circulation. And as you learned before, the surface circulation, we're talking about horizontal flows, which are the strongest near the surface and then disappear at depths below 1 to 2 kilometers. Horizontal currents that are indirectly created by the wind stress. Again, you can identify the largest coherent structures in the ocean, which are called gyres. And you can see that there are subtropical gyres both to the north and the south of these areas here. And they have a western boundary current on the western side. Okay, in the northern hemisphere, there's the Kuroshio, and in the southern hemisphere, the East Australia. And these western boundary currents, they have speeds of more than 1 meter per second. In the North Pacific Ocean, there's also a pronounced subpolar gyre. Okay, it's also produced by the wind, indirectly by the wind stress curl. Okay, and on the western side, it has the Oyashio. On the western, it's the western boundary current. Okay? And what these currents do is in the North Pacific is they produce, actually, one current comes from colder waters, and one comes from subtropical, tropical regions with warm water, and they actually meet and they create something that we call a frontal zone. That's a region of large spatial gradients of temperature. It's the polar front that is. Okay, so what else are features here? On the eastern side, we have current systems which are created or influenced by coastal winds. The California current, Peru-Chile current here in the southern hemisphere. Near the equator, it gets really complicated because we have countercurrents near the equator. We have the currents which are linked to the gyres, like the North Equatorial Current and the South Equatorial Currents, but we have countercurrents. We also have undercurrents, and I'll show you the structure in a few minutes. Okay, and then in the Southern Ocean, we have the circumpolar current that I made. Okay, these are the key features. These are the key features of the wind-driven circulation. But let's have a look first at the Kuroshio-Oyashio current. Okay, it's a very fascinating region because these two boundary currents actually meet. Okay? And this is how this zone looks like. So what's shown here is the pathway of surface drift. Okay, so these are GPS drifters that you check into the ocean. They communicate with satellites and send the geographical coordinates. Okay, and from that you can determine the location where these boundary currents meet and also the mean pathway. Okay, so you have the it's shown here in the sketch. You can see the Kuroshio comes from the south, creates something which is known as the China meander, okay, and creates the Tsushima current and the Sugara warm current. Actually comes here back on the northern side of this island. Oyashio comes from the north. And all right, and they create something we call meanders. The first crest, the second crest, and then there are some interactions with seamounts and stuff. But from many floats, you can see the pathway. It's actually the water becomes deflected mainly zonally to the east. That's all there is. And it creates eddies. We talk about eddies later on, and so on. Okay, but there is no significant transport of warm water from of the Kuroshio into the North Pacific. This is a significant difference to the North Atlantic, where we saw that there's warm water even injected into the Arctic Ocean. And that's a big difference. So here you find a very clear transition zone between cold polar water and warm tropical